So for number 3 on page 16, it says that the combustion of 1 mole of sucrose evolves 5.65 times 10 to the third kilojoules of heat. So I'm going to write it over here. 1 mole of sucrose. When it says it evolves, that means it produces 5.65 times 10 to the third kilojoules of heat. And since it's producing the heat, that means it's releasing heat, so it's going to be negative. Now that's going to be some useful information for a little bit later. It says a bomb calorimeter with a calorimeter constant of 1.23 kilojoules per degree Celsius contains 0.6 kilograms of water. How many grams of sucrose should be burned to raise the temperature of the calorimeter and its contents from 23 to 50 degrees Celsius? So, for any calorimetry problem, it's going to be very important that we focus on the different systems that exist. Now we know it's calorimetry because the problem says a bomb calorimeter, so it's telling us that it's a calorimetry problem. Now when they give us a calorimeter constant, we have to focus on Qcal as one of the systems. So one of the systems that we have to focus on is the heat absorbed by the calorimeter. So Qcal is one of our systems. It says that in the calorimeter there is also water. So water is another system. And it says that we're burning sucrose. Now whether you want to do Q of sucrose or Q combustion or Q reaction, I don't care how you name it. I'm just going to put it over here off to the side. I'm going to do Q of sucrose. If you look on my answer key, it says Q reaction. It doesn't matter what we do. We're solving for the same thing. So we have 3 systems that we're focusing on in this calorimeter. The first law of thermodynamics says that all of these heats have to add up to equal 0. So all 3 need to add up to equal 0. Now this is a little bit more of an advanced calorimetry problem even than what we were looking at yesterday because it wants us to calculate grams. Now to start, before I worry about how many grams need to be burned, I want to figure out how much heat this sucrose is producing. Because we're trying to figure out how much is being burned. And so we need to know how much heat do we have. So we're going to solve for Q of sucrose. If I'm solving for Q of sucrose, that's my variable. That's what I'm solving for. Which means I'm going to go ahead and plug in variables for Qcal and Q of H2O. When you have the calorimeter as part of your problem, when it's one of your systems, Qcal is calculated a little bit differently than Q of H2O or Q of anything else. Qcal is just Ccal times delta T because the calorimeter constant already takes into account the mass of the calorimeter. So when you have Qcal, that's just Ccal delta T. Q of H2O will be MC delta T. So it's normally MC delta T unless you have Qcal. That's when it's a little bit different. So again, we're solving for Q of sucrose. Now I'm going to plug in numbers. Ccal, that's the calorimeter constant. It tells us that the calorimeter constant is 1.23 kilojoules per degree Celsius. Delta T is always final minus initial. And so the final temperature, it says, was 50 degrees. The initial was 23. So delta T is 27 degrees Celsius. Delta T is the same for the calorimeter and for the water because everything is inside the calorimeter. Then we have MC delta T. And we have to be careful. They give us mass in kilograms. So I'm going to kind of separate. They give us the mass of water as 0.6 kilograms. It needs to be in grams to put into MC delta T because the specific heat of water is joules per gram degrees Celsius. So remember, there are 1,000 grams in a kilogram. You don't have to necessarily show this work, but you do need to make sure you have 600 grams. Specific heat of water is the one specific heat that you need to know. 4.184 joules per gram degrees Celsius. Delta T is 27 degrees Celsius. This entire thing equals 0. I just moved the 0 over because I ran out of space. Now, I want to look at canceling some units really quick before we plug things in. So notice kilojoules per degree Celsius and degrees Celsius. So the degrees Celsius cancels, which means this value of Q is in kilojoules. Over here, we have grams cancel, degrees Celsius cancel. This value of Q is in joules. We just need to keep that in mind as we continue with the calculations. So, we're solving for Q of sucrose. 1.23 times 27 is 33.21. Again, this is kilojoules. Plus 600 times 4.184 times 27. 67,780.8 joules. So before we can add these two like terms together, they need to be alike. They need to have the same units. I would recommend putting your joules into kilojoules. It's easier numbers to work with. Remember that there are 1,000 joules in 1 kilojoule. So this is 67.7808 kilojoules. Move the decimal place over 3 times. 1, 2, 3. Kilojoules are easier numbers to work with. They're smaller numbers. So now I'm going to combine like terms. Q of sucrose plus 100.99 kilojoules. So I'm going to solve for Q. What is Q if I rearrange this equation? It should be negative 100.99 kilojoules. Now this is Q. This is the amount of heat that is released when a certain amount of sucrose is burned. We don't know what that certain amount is. That's the point of this problem, is to figure out what amount was burned. Well, they gave us delta H. They gave us delta H up here. That's kilojoules per mole. So what we're actually going to do is we're going to do a stoichiometry problem, essentially is what we're doing. We're converting units. We're using delta H as a conversion factor between kilojoules and moles, which we can then do to grams. So let's start with our value of Q. Negative 100.99 kilojoules. I'm going to go from kilojoules to moles using delta H. Then I'm going to go from moles to grams using another conversion that we know. So again, what I'm doing here is I'm taking Q, I'm using delta H to convert to moles, and then I'm going to use the molar mass to go to grams. We're essentially going backwards from the calorimetry problems that we've looked at before. So, using delta H for 1 mole of sucrose, it releases 5.65 times 10 to the third kilojoules. So now my kilojoules have canceled. I'm at moles. To go from moles to grams, we're going to use the molar mass. 342.29 grams is 1 mole. This is the molar mass of sucrose. So we used Q to start. We used Q as a starting point. Delta H allowed us to convert between moles and kilojoules. Then we used the molar mass to get to grams. So if we go 100.99 times 342.29 divided by 5.65 e to the third, we get 6.12 grams. Now, another way that you could have solved this is you could have set this up like a proportion. So another way is we could have used Q and delta H and set it up like a proportion. So we could have said we have negative 110.99 kilojoules for X number of moles, and then use delta H. Negative 5.65 times 10 to the third kilojoules for 1 mole. You can solve this. So because you have this equal sign, it's a proportion, you can cross multiply. You can solve for your moles that must be burned to produce this amount of energy, and then go to grams. So either way, either the proportion or stoich. So because Q and delta H are negative, those will cancel out. Just remember that masses should always be positive. You cannot have a negative mass. So if you're solving something and maybe you forgot the negative here, and you get a negative number for mass, just remember that that has to be a positive number. So this was taking a calorimetry problem that we looked at yesterday. So now if you actually look at this, if you do negative 100.99 divided by 6.12, there is your kilojoules per gram. Multiply by the molar mass, that's going to give you the